There's like 17 mice on the screen.
Yeah, let me try to fix that real quick. Like I said, there's not a great way to do this, unfortunately, without hiding the without hiding those outputs. Okay, let's try this again. Cool. So you should be able to see those outputs, right?
Mm-hmm.
Right. Okay. I think that's as close as we're gonna get. So hopefully y'all all got a chance to at least look at the motor control code. We're gonna go through that, talk about how to program that. Then we're actually gonna test it, and then we're gonna move into introducing the HMI software. So I've been firing off new homework assignments like crazy, as I'm sure you've all seen. Hopefully you got a chance to at least install the Seymour HMI software, because we're going to go over that today. It is not currently installed on the VMs. So if you don't have a way of getting into that software, let me know now, and I'll try to bug them and get that installed. Unfortunately, right now the way it works is you have to buy a license. They're gonna make the software free going forward, but they're not going to do that until the next release. And so for now, we don't have a way. So you don't need a key code to install the software. You can install it in demo mode and then activate it. And so later on down the road with a key call. So if you have it installed, please email me, and I'll give you some more instructions on how we're going to handle the demo version until they do the next software release. If you cannot install it because you're using a Mac or something, also let me know, and I'll look into options for getting it maybe installed on the VM cluster. Okay. So I've also started creating some optional homework assignments. I'll name them optional so you can tell. That's for those of you that are like putting a lot of time into this and want more programming challenges. It's fun stuff to program. I know a lot of you have senior design stuff due. You're in the same boat as me right now. So I know this week's probably going to be a little bit light on participation. No worries. Just let me know if you need, like if the homework won't be turned in on time and I need to extend a deadline or something. That's no problem. Okay, so without further ado, let's go through that motor control program that we talked about. So I uploaded code that covers the first part of assigning the VFD speed, right? So hopefully you took that and rewrote it in a way that'll use the counter and timer in order to calculate RPM. So I'm going to step through how to do that code right here. And I just got to look at my reference stuff first. Okay, so this timer is counting up, right, as soon as it's activated. So the way this is written right now, this timer is just going to start counting up until it hits 10 seconds, and then it's just going to be done counting. So the first thing we need to do is make it so that it resets itself when it's done counting, right? And so we can do that by adding a normally closed contact, and we'll just make it T1 on that rung. And so what that does is every time this counter finishes counting up and hits 10 seconds, it's just going to reset itself immediately. So that's all well and good, but we want this counter and this timer to basically be operating in the same time space. And so if our timer gets reset, we're looking at a new chunk of time, which means we need to reset our counter as well, right? So to do that, we can come in here and add that rung on the reset and add add a normally open contact, and also make that T1. And so whenever our timer reaches completion, it's going to fire off and reset the counter back to 0 as well at the same time. Okay. Which means that, let me look at my code again to remember what I did.
I have a question.
Yeah.
So when the timer is not enabled, that means that it resets to its initialized value or something? Why does that T1, why does that cause it to reset?
Oh, okay. So the way this timer block works is it'll count up until it reaches the set point. And right now our set point is 10 seconds, right? So once it hits 10 seconds, that T1 output is enabled, and the timer would just stay in that state where it's like, I'm done counting up. I've enabled my output. I'm done. I'm not doing anything, right? And just stay there. And so what we want is we want that to reset periodically. And
Yeah.
in reality, like, sorry, go ahead.
No, I didn't.
So
That's
the
it.
reality of the situation is that if we could have this counter count indefinitely, we could just leave it alone and never reset it. But the problem is we're limited by memory registers, right? There's a finite size to the size of the number that we can count in the counter and the timer, right? Eventually that memory is just going to fill up and the number is going to be too big and we can't count up anymore. So we need it to periodically reset itself. And we could pick something bigger than 10 seconds. It doesn't really matter though. So you'll see why in a little bit. But basically what I'm doing is making this timer reset itself. And I want it to be synchronized with the counter. So the counter is going to reset as well. So
My question is, why does that reset it?
Oh, why does it reset it?
Yeah.
So this is a normally closed block, right?
Yes.
So if this is not, if the state of this bit is 0, right, it's not active, then this rung is closed and energized and the counter is enabled.
Yes.
Okay? So as soon as the timer finishes counting, the output will fire and that contact will open for one scan. But when that contact opens, the counter becomes disabled and the value is not retained. So it basically resets the value to 0. And then on the next scan, it'll immediately reset or start counting up again.
Okay, that makes sense.
Yeah. Sorry, that wasn't very clear. And so the other thing we got to do is we want these to kind of be self-consistent. And so in the event that this counter counted all the way up, which is possible, we want it to also we want it to reset itself, and we want it to reset the timer. So I'm going to add a parallel rung here on the reset for the counter, and I'm going to add a normally open contact for CT2 for that counter. And I'm going to add another normally closed contact for the timer. So basically, if this output, the CT2 output activates, then both the counter and the timer will be reset. Okay. And then the last thing I want to do is, if you guys remember from last time, X104 is my e-stop input, right? And so if I hit that e-stop for whatever reason, that's the big red button, right? The big red mushroom. Then I probably want to reset my counters and stuff too, because that means I had like a fault in the system and I want everything to reset back to 0. So I'm just going to do the same thing where I add another parallel on the counter reset. Make that X104. And then I'm going to add another normally closed here on the timer. And that functions in the exact same way as the other two we just did. Forgot to plug in my laptop. Okay, so this pretty much works these two blocks will start executing as soon as you energize the controller, essentially. And so we're kind of assuming here that we're going to start operation from an e-stop state. And so, sorry, I'm trying to pull up the chat. Somebody had a question here. Okay, so if you add a value contact, so the timer will only start when CT1 is greater than 0. That's a great idea. That's a really good idea. So what Mason said is basically add a Boolean contact. And so I was going to use a Boolean contact for something later, but that's a great idea. So what we'll do is if you add the comparison, so what we're doing is data A. So this comparison block, basically, it's a normally open contact that closes if the Boolean operation evaluates to true. So data A will be CTD2, okay? And we'll make that, if it's greater than 0, then this block evaluates as true, okay? And that's a really good idea, Mason. I was gonna do something a little bit different, but this works really well. So basically, if our counter's 0, then our timer won't operate. If our counter's bigger than 0, our timer will run. And then this stuff is all kind of like self-managing because every 10 seconds that timer is going to reset, and it's going to reset the counter back to 0. So that's a really slick way of managing this, actually. And that's one of the advantages of using a fairly small timer reset time. So using 10 seconds fairly frequently, it's going to reset and basically self-check. So ultimately, where we're going here is we want to use that to calculate the motor RPMs. And so actually, the only thing we really need now is a math block to do that calculation. And so in adding this math block, so I'm trying to remember if there's a specific point. Oh yeah, you guys can't see that screen. One second. Let me set up the view screen again. Oh, that hurts to look at. I apologize for my technical difficulties, guys. There we go. Okay, so now you can hopefully see all this fairly well. Okay, so we're gonna add a math block in there. And now you can see the pop-up. Cool. So I need to assign a point in space to store this value. And I want to get
can't see your shared screen.
Yeah. That's because I forgot to share it again. Sorry, guys. I'm learning this as I go. Okay. Now you can see my screen, right?
Yeah.
Awesome. Sorry about that. Okay. So now I need a math block to calculate my RPM. So when you put in a math block, it has to write a value somewhere. And now that I'm thinking about this, and really, it doesn't matter if our RPM is a decimal. Like generally, you read RPM as an integer value. And so I'm just going to make this a DS. And so a DS is just it's an integer data storage point. It's arbitrary, and you can just start with DS1. There's no like rhyme or reason to how that's assigned. Whereas if we were using a floating point value, if you look here, all these are already used, and that's because they're actually associated with physical IO. So you need to be, if you are assigning DF values, you need to be careful and assign higher values than what your actual physical IO is using. So we're just going to use DS1 because it's easy. Okay. So now, what math do we do to calculate our RPM? That was actually a question, guys. Where's the chat? Yeah. So that's good. So we're doing revolutions per RPM. Yeah. Okay. So CTD2, right? That's our count of our revolutions divided by TD1, right? TD1 is our time count. And then the units of TD1 are milliseconds. So to convert to minutes, we just need to multiply it by 60,000 exactly. And that should give us rotations per minute. Okay, so this math should work. And it'll assign this value. So I think this should work. So let's test it. So I'm going to write. I got to connect to the PLC first. I forgot to reset the breaker. Give me 2 seconds. Sweet. We're in business. Sorry about that. I'm fighting the wiring in my house to actually be able to run this motor. Okay. So let's try to go online. Okay. We're online with the PLC. Gonna write our code in. Oh.
Real quick, what type of contact is that has the up arrow in it?
So this is the differential contactor. It's
Oh,
basically, so if y'all remember when Bill went over his in Bill's presentation, he had a lot of things where basically it's like a contact and this axis is time. And so you'd have the state could be 0 or 1, right? And it would start at 0, and then at some point it would go high for a while, right? And then it would drop back to 1. So this is like an input on the PLC, or this is representing an input. And at this point in time, T1, the input gets activated or energized. Okay, and then at this point in time, T2, the input is deactivated. And so what that differential contact is looking at is basically when it gets triggered. And so that'll go on, the way it's written right now, it'll go on at T1, the first point in that square wave. And then if you were to do the one with the down arrow, it would trigger off off T2 when the output goes down. And that's called triggering off the rising edge or falling edge. It's good to do in cases like this where you want to count as soon as the flag breaks the beam, right? As soon as that flag goes in between those two forks like that and breaks the beam, you want it to count up. It's not really that critical in this case because we're spinning so fast, but it could potentially be an issue if like you have a box going down a conveyor belt and then you have a laser. And when does it count on the regular open contact? So yeah, so if you have a box going down a conveyor, you might want to trigger off the rising edge because as this box is going, it's going to break that beam for a long time. Or you might want to trigger off the trailing edge because you're using this laser. When it gets unblocked, you like release the next box or something. So that's where using those differential contacts can be really important. I had a question: when does the count trigger on a regular open contact? I think it's just I think it's on the rising edge. I can't tell you for sure. And when I tested this with just a regular open contact, it actually functioned fine. You don't actually have to use a differential contact. But I did anyway because it's kind of best practice. Okay. I think that's all the questions that we had coming in. So I'm going to, oh, what was the warning? Run 1. Oh, I screwed up. This subroutine shouldn't be here. So that warning that I got when I tried to write the file, it was because I had an artifact in my program from when I was playing around with subroutines last time, and I left it in there. So that's why it threw that warning. I'm gonna hit my e-stop because that's always best practice before you download something. Make sure you're in as safe of a state as possible. I'm gonna go ahead and do runtime though. Okay. Which screen am I sharing right now? I'm sharing 2. Okay, there we go. So now I'm gonna take the e-stop off, hit my activator. Okay, so from this code, it looks like I should be good to go. I'm gonna hit up count 1, and then it looks like it is cycling, but this counter is not counting up. Why is X104 active? That's weird. That's really weird. Oh, I know why. Maybe not. The e-stop is normally open. So I think I may know what's happening here. That's really weird. I'm not sure why that's being triggered like that.
Well, wait, don't you have it coded in as normally closed?
Yeah. So yeah, so this basically means that it's activated, like it's receiving an input, which it shouldn't be. This is really weird. I'm gonna delete this rung here and see if that fixes it, because that's preventing our counter from counting up, which is preventing anything else from happening. There we go. Okay, I'm really not sure what's happening with that e-stop, why its reading is active like that, unless we have a short somewhere. So I'm gonna have to mess with that later and get that figured out, because that was not happening earlier. But if you look at the code, it's slowly counting up. Now this is right now our VFD is set to 10% of its running speed, right? Which means that if our max motor speed is about 1725 RPM, 10% of that should be about 170, 175. And so if you look at this math block as it's live calculating, we're in that ballpark, right? That seems pretty reasonable. Now, because of the way we've programmed this at low speeds, our revolution isn't super great, but it should be good enough to get at least a ballpark, which we have. So it looks like this is working. So let's try it at slightly higher speeds. So I'm going to take it up to 50%, and we would expect that to hit at about what, like 850 or so, which it looks like that's where it is. So one thing you'll notice is that this is kind of jumping around a lot. And it has to do with every time this resets. And so what we can do is we could add another Boolean block here that basically prevents this math block from executing unless our count is at a certain number. And so basically what that would do is prevent the RPMs from being reset until we've counted up to like 100 counts or something, where we know that RPM calculation is going to be more stable. And so all you would do is in here write another conditional block and say CTD2 is greater than let's just say 100, or let's say 50. That's reasonable. So we just gotta go ahead and kill the system, hit the e-stop, re-download. Reset the e-stop. Yeah, this is where we really need that. We really need that e-stop contact to reset everything. That's okay though. We'll just let it run out and reset itself. So you can see now that RPM value is a little bit more stable. It's kind of staying put in the 880, 890 range. And so you can see the way that we did this conditional block, the Boolean block, it's probably not the absolute best way to do it, but it definitely works. So there you could do some like some pretty tricky math where you took like the VFD set point and did some math based off that to determine the conditional value in data B. But this works fine for our purposes. It's probably good enough. So just for funsies, let's take it all the way up to 100%. That thing's really, really cooking. So at 100%, what would you expect this this RPM to be? Anybody know? The max, right? So somebody said 1776. Merca. So this motor that we have from the vendor says that it's rated for the max RPM is 1725 on this motor. So there's a couple things that could be happening here. One, our VFD could be a little bit out of whack, and when it says it's putting out 60 hertz, it's actually putting out slightly above that, right? Like 60.2. That's a possibility. Another possibility is that there's something a little funky in the voltage in my house. Although that goes through the conditioning in the VFD, so that may or may not be the culprit. The other thing is that, you know, this isn't like a high precision stepper motor, and so more than likely what's happening is just that you know, the windings are just a little bit off inside this motor, and it's just causing it to run a little bit fast, right? So we're calculating that this thing is spinning in the ballpark of 50 RPM faster than what it's rated for, which I think is actually true. I think our counting system is actually pretty good here. So that's kind of a good to know, right? Because if you just built a system assuming that this thing is spinning at 1725 RPMs, you'd be going a little bit faster than you thought, and your calculations would be a little bit off. It's not enough. So what percentage is that, right? That's like, it's very small. Let me calculate this real quick. So 17, let's say 1780. So that's like 3% fast, right? It's not that much, but it's enough to where that's probably outside of, you know, a 1% calibration value. You duct tape your car? Yeah, 100%. If you adding tape to anything increases the horsepower every time. It's a surefire way. So that's I think everything we can do. I guess we could add another tape flag onto the motor, and then we just add a factor of 2 in our math. It pleases the tape gods. So we just add a factor of 2 in our math, and we could increase the resolution of this counter a little bit. But this works pretty well. I'm pretty happy with it. So I'm gonna bring the speed back down. I got my own personal little fan out here. Okay, so the next thing I want to show before we end today is the HMI software that I had going, or that I asked you guys to download. While that's booting up, I'm gonna start the HMI. So what I've been doing is actually playing around with this a little bit. And I figured out how to do some virtual switches and a few other things. So I'm just gonna show you what those are real quick, because we only have like 10 minutes left. And I know everybody's a little strapped for time. And then we'll get into this in more detail on Wednesday. But basically, the way these screens work is you're just creating virtualized things on this screen, and then you tie the touch screen together to the controller with what's called a tag. And let me switch screen I'm sharing. Go to screen 1. So what you can see here, where my hand is this is the screen that's actually downloaded on the HMI and running right now. And so if I go into the configuration software and I open up this motor contactor that I've programmed, there's a tag called switch 1 status. And that's just something I made up, and it's a bit in memory, so it's either on or off. And that tag, the status of that tag gets toggled on or off when you press this switch. So when I touch the switch on the screen, that toggles that tag on or off. And what I've done is written some code in here where
there's a big gray bar on the screen now, like a long horizontal box.
Did I get rid of it?
Yeah.
Yeah. Okay, cool. Sorry about that. So if I go here, so what I've done is I've tied what you do is to tie tags together. In the PLC, you make a nickname, and then in the touchscreen tags database, you just create that same nickname in the tag database. So you just hit add, and then you tell it what the address is in the PLC. So what I've been doing is, in the order of creation that I follow here is basically put the tag in the PLC, name it, assign the data type, and then go into the touch screen and create the corresponding tag in the touch screen in the exact same way it's created in the PLC. Okay. And so let me download this code into the PLC, and you'll be able to see that as you toggle this switch, it'll toggle this bit on the PLC. And the other thing is you see this data type is a C. C stands for contact. And what that is basically a virtual contact in the PLC. So before we've been using like X's and Y's, right? And those are tied to physical IO on the PLC. Well, for tags, for bits that are associated with tags that go between the touchscreen and the controller, we want to use the C-type bit because it's a virtual bit that's not tied to any physical hardware, and so it's kind of free to use. We don't have to worry about having conflicts between our physical I/O, which I think is what it was happening with the e-stop earlier. Okay, so that program's written in, and now if I touch the switch, you can see in the code the C1 bit got toggled. Dang, dude. That e-stop is acting funky. I gotta see, it might be physically shorted in the panel, actually. Yeah, I think that wiring is actually shorted in the panel. I gotta go through and retouch all the wiring. But anyway, you can see how that works. So the way I have this set up right now is to, when that switch is on, I'm gonna light up Y101, which is the motor contactor circuit to be closed, and then I'm also gonna light up Y002, which is just that that white light, which kind of tells us that we're set up to run. So the other thing I've done in this code is that I have the same math block calculation, but instead of using our push buttons to go up and down with the for the motor speed, what I've done is configured it so you can actually just click here on the screen and use a touchpad to type in the speed, and it takes that value from the screen and writes it into a data register in the PLC, and then this copy block just copies it from that data register into the output to the VFD. And so that way you can control your VFD speed. And so now you can change that percentage to any number you want. It doesn't have to be in blocks of 10, simply by typing it in on the screen. And then the last thing I did is I wrote a math block that does the RPM calculation and then writes it to a register that can be read by the touch screen that'll be displayed right here. And I really wish I could show you that, but for some reason, this e-stop block is activating. I do not know why. But because of that, none of this is running. Oh, there we go. I take it all back. Cool. So it's actually working. So you can see that RPM value is being constantly updated. And we definitely need to do what I was talking about before, where we stabilize this. We use a fancy math block to stabilize this so that value doesn't jump around as much. So that was kind of a stumbly overview of what we can do with this touchscreen. On Wednesday, I'm going to go over how to set up those communications, how to set up the touchscreen, and then demonstrate how to create some of those blocks. But that's what the next homework assignment project we do will be, using that screen. Sorry about all the technical difficulties today. I really thought I had that stuff ironed out, but I'm having to actually rewire a socket every time we meet in order to be able to actually run this this motor off my home electricity. So that's where some of those problems came from. That's all I got for today. Anybody have questions? Does everybody feel pretty good about the homework?
Yes.
Super good.
Super good.
Best.
The best.
Does anybody have concerns about time conflicts with senior design?
That's why I have a group.
Yeah.
Yeah.
Our
So-
kinetics is whack.
What's that?
Our kinetics is whack.
Oof.
Oh,
That's really important.
sorry. I don't have to worry about that because they just gave me my kinetics.
What now? That was like the hardest part.
Are you kidding me?
No, I'm not kidding.